So here is the outline. We will introduce the what is the current. And the current density. The current density is actually like a surface integration, and the resistance and resistivity. And we'll talk about the Ohm's law, and for easy student users have learned it in circuit analysis. But we will see it in another hardcore physics point of view. Although you don't necessarily need to know it very well, because it is just another point of view to explain why Ohm's law will be like that. Actually, it is not accurate at all. So, and then we'll briefly explain the power, semiconductor, and superconductor, which is we just scratched the surface of this topic. So for electric current, so any isolated conducting loop, regardless of whether it has excess charge, is all at the same potential. So no electric field can exist within it or along its surface. So isolated conducting loop. So there will be no potential difference. All the points will have same potential. So now we try to do something not so easy. So we try to insert a battery here. To make this loop a bit broken. Of course, you try to connect it at this point and this point. So if we insert the battery in the loop, the conducting loop is no longer at a single potential. So electric field acts inside the material, making up the loop, exerting force on the internal charges, causing them to move and thus establishing a current. So as much as you have a battery here, so that the electric potential at this point will be higher than the electrical at this point. So we will expect a current going from here to here. Okay, so So the current is the same in any cross section. Even though you try to make the wire as strange as this, so it is thinner at this part and thicker at this part. But the current going through this cross section, AA prime, BB prime, and CC prime will be the same. Otherwise, there will be some charge accumulate at this point, which is not allowed. Because we have the definition here, I to be dq dt. Actually, I think in chapter 21, at the very beginning, we already seen this one. Actually, we use that to define the charge, and now we use it to define the current, which is very strange. Yeah. So you don't really know who comes first. So here, a section of conductor part of conducting loop in which current has been established. If charge EQ pass through a hypothetical plane, which means imaginary, which doesn't practically exist. Just formed by imagination, such as AA prime in time dt, then the current I through that plane is defined as this one. So which means that for every time there will be same amount of a dq going through this plane for every dt to make this I to be constant. So nothing special. And next, we also introduce a law called the Kirchhoff current law, KCL. KCL is in circuit is stand for the Kirchhoff's current law, not potassium chloride. It is chemistry stuff. So a conductor with the current I0 splitting at the junction in two branches because charge is conserved. So we know charge is conserved. In chapter 21, you already know this fact. The magnitudes of the current in the branches must add to yield the magnitude of the current in the original conductor, which means, so you can see it here. There are three branches connecting to the point A here. So actually I0 is going into this node and I1, I2 is going out from this node. So according to the charge conservation, which means charge conservation, yeah. So in that case, I0 must be I1, my I1 plus I2. So the current going in this node, or the sum of the current going in this node, will be equal to the sum of the current going out from that node. Yeah, so like that. Usually I will not. Yeah, usually my habit is not memorizing the KCL like that. Usually I will just count all the current. I will just count all the current going out or going in a node. Sum up currents. All the currents sum up to be zero. Sum up to be zero, because if you consider sum of the current in and sum of the current out, then you need to distinguish which one to put in the left hand side, which one to put at the right hand side. Then you'll probably have more chances to have correct incorrect sign, or incorrect or -1, something like that. But yeah, my habit is to just keep all, yeah. For example, if a circuit like that, usually I will just count all the current going outside. For example, this one is VC, V1, V2, V3. I will just write this is R1, R2, R3. I will just write it as VC minus V1 over R1 plus VZ minus V2 over R2 plus VZ minus V3 over R3 equals 0. So you don't need to bother, this one is going in, that one is going out. Then yeah, you need to put it in the other side, and then you need to swap the order of the subtraction. So this one is very, very symmetric. Then you don't need to care about the sign. Yeah, it makes you have less chance to make mistakes. Okay, so next is the current density. The current density, yeah. So this definition is also very strange, because usually for definition, when you try to define a variable, let's say x, it should be something like x equals to something else, f of something else, a function of other stuff. X equals to something will be usually a definition. But now we try to define the current density with this integration, but we put this current density on the right hand side rather than the left side. So here we try to define the current density J, which is a vector. I is not a vector. Current is a scalar. Although you can say the direction of a current, but current is a scalar. This is a vector. So to define it, you will try to have a surface, don't need to be close, and then you try to work on this surface integral j dot dA, and then do the surface integration, and then it will be the current of that surface you concern. So we just like suppose you have let's say this is the surface you like to concern, and then there will be some current density going through it, and then of course, similar to the Gauss law, you need to define the dA, which is the vector surface perpendicular to the surface at that point. And of course, this is not a closed surface, so you can design dA point to the this side or the other or the opposite side. So it's just up to you. But if it is positive, which means that the current is going to if we define dA to be pointing to the right side, that means if I is a positive, then the current going to the right side, and vice versa. So dA is the vector perpendicular to the surface element of area dA, and the integral is taken over any surface cutting across the conductor. So the current density J has the same direction as the velocity of the moving charge if they are positive charge. So yeah, this is the point. So because at that time, the physician or the scientist has not discovered electron yet. So at that time, they define the current, assuming the moving particle is the positive charge. So when you consider the direction of the electron, the moving direction of the electron, then it is the other way around. So the opposite direction, if the moving charge are negative, of course we know now the moving charge should be the electron, which is negative charge. Actually, in chapter 28, we will chapter 28, we will learn one thing called the Hall effect, which is an experiment to show that the moving particle inside the conductor should be negative charge rather than positive charge. Yeah, so you will learn it in the next chapter. Okay, so here it has something like hardcore physics. When I learned the physics, the professor also told that, oh, this is very important, but yeah, probably we will be useful in physics, but not engineering. So I just try to explain it, because the professor said that it's very important, but actually I seldom use it later on. Yeah. So here it says conduction electron are actually moving to the right, but the conventional current I is set to move to the left. So we define I pointing to the left side, which means the electrons are moving to the right side. But here, it just assumes that the moving particle is positive. In this case, it doesn't really matter whether it is a positive charge moving to the left side or negative charge moving to the right side. It gives you the same conclusion. So let's just keep the moving particle goes to the left side, following the direction of the current. So here, charge in the volume AL. So the cross section, A is the cross section, and the length is L. Length is L. So A is the cross section. So AL is the volume of the wire that is for this part. So so here N, small n is the density of charge particle, density of charge. So NaL will be the number of charge inside this area, and then multiply it by the elementary charge. So this is the number of charge. So number of charge times the elementary charge, which is the total charge in this volume. So time to go through L. Time to go through L is T equals L over Vd. So we assume the velocity, the drift velocity. So Vd means the drift velocity of the charge. So L over V is the time. So very, very simple. Primary students should know this. So so the current I equals Qt, because we just assume that the velocity is constant. So I equals Qt dq dt, just shrink to this case if it is a constant. So Q over T, Q is this one. So T is this one. So we just divide them, and we have N times E here, and then A, B, D. L and L can be cancelled. So we have A times BD, like this. And also just now we have I equals integration of J dot dA. Now we also assume that the current density is uniform. So it is nothing but J times A. Suppose J is uniform and perpendicular to dA. So it is I equals JA. So J equals I over A. So I over A, we can just divide A on both sides, and so this is J, and A can be cancelled. So we have J equals N times E times Vd. So which is like the J is proportional to the drift velocity. So this is the density of the charge. You can really change it. And E is the elementary charges, which is of course a constant. So we have the current density proportional to the drift velocity of the charge. Okay, so current is said to be due to positive charge that are propelled by the electric field. Positive charge carry drift velocities bit Vd in the direction of the applied electric field, which here is applied to the left. By convention, the direction of the current density J, blah blah blah. So the product Ne, whose SI unit is the coulomb per cubic meter, because this is the N is the density, the volume density of the charge, and then times the elementary charge. So it will be the charge density, charge volume density. C over meter cube is the carrier charge density. So this is a constant for a specific material. For different material, this constant will be different. Okay, so here, let's see a sample problem. So the current density in a cylindrical wire of radius R, capital R, is uniform across a cross-section of the wire, and J is this value. What is the current through the outer portion of the wire between radial distance R over 2 and R? So this graph only shows the cross-section for the wire. for the Y, cross section for the Y. So it asks you to find the current going through this part only. It only asks you to find this part only. Although J is uniform over the whole wire, but it only asks you to find that part. So actually, I for that part will be J dot dA, but of course it will be a constant. So it is nothing but. So yeah. So let us find A first. Yeah. So A is actually the area of the outer circle minus the area of the inner circle, which is pi r square minus pi half of r quantity square. So which is 3/4 r square pi, like this. So this is nothing but 3.14 times 3 times r is 2 millimeter, which is 2 times 10 to the minus third quantity square over 4. So this is 9.42 times 10 to minus 6 meters square. Okay, so next we can plug this value here. So it is like I equals J times A, which is 2 times 10 to the minus 2 times 10 to the fifth power. 10 to the fifth power times 9.42 times 10 to the minus 6 power, which is 1.98. So it is very easy, just algebraic calculation. So the next part is more difficult. You need to use the integration. So instead, the current density through the cross-section area vary with the radial distance. So J is not uniform anymore. J is proportional to the square of the radius. So in which A is this value, R is in meters. What now is the current through the same outer portion of the wire. So here we need to calculate, same outer portion, which means from R over 2 to R, like that. So here we have I equals integration of J dot dA. Okay, so as much as J is parallel to the dA, so this is just JDA. So we don't need to consider the direction. Next, J is actually the surface integral. So J is AR square. So we have AR square here. And of course, we would like to integrating this from R over 2 to R. So probably we should use the polar coordinate. So polar coordinate is like this is R theta. R is larger than 0. Theta is between 0 and 2 pi. Between 0 and 2 pi. So this is theta. This is R. Something like that. So so for dA is something like this is R. This is R. So this point is R theta. So this will be dr, and then this is theta. So we move a little bit here. So this angle is d theta. This area, and this area will be our dA. Will be our dA. So as much as dr and dA theta are small enough, although this is not a rectangle, but if dr d theta is small enough, you can approximate its area as a rectangle. And so it is like this side multiplied by this side or this side. So this side is dr, very trivial. And for this side, in high school, I suppose you have learned that this side should be r d theta, or at least the inner part is like that. But if it is small enough, this side should be equal to this side. So this is a rectangle. This side is dr, this is r d theta. So dA will be dr times r d theta, or usually we'll write it as r dr d theta. So we have a times r dr d theta, and of course r we need to integrate from r over 2 to capital R. Yeah. And then for theta, because it is a whole circle, we need to integrate it from 0 to 2 pi. So this double integral is easy because we can just separate the variables. So we have A is a constant, so we put it outside. And then we have R cubed here. So dr, and then R over 2 to R. And then d theta, which is just 1, 0 to 2 pi. So this is easy. This is 2 pi. This is r to the 4th power over 4 evaluated from, sorry, it should be small r. Should be small r. Small r to the 4th power over 4 evaluate from r over 2 to r, like that. So this is nothing but a, and then this is r to the 4th power minus 4 minus r over 2 quantity to the 4th power over 4, like this, times 2 pi. So using slightly simplify it, it is 15 over 32 times a times r to the 4th power times pi. So we can plug in the value. 15 over 32 times a is 3 times 10 to the 11th power, and then times r. What is r? R is 2 millimeter. 2 times 10 to the minus 3rd power to the 4th power, and then times 3.14. So the answer will be 7.18, like this. Okay. So next is another sample problem. So it says what is the drift speed of the conduction electron in a copper wire with radius r when it has a uniform current I. Assume that each copper atom contribute 1 conduction electron to the current, and that current density is uniform across the wire cross section. So in Appendix X, we need some value, density of the copper. This is gram per cm cube, and molar mass of copper, 63.54 gram per mole. Wow. So some chemistry stuff, and then Avogadro number, Na equals 6.02 times 10 to the 23rd power per mole. Okay, so here we need to we need this equation. Yeah, actually you can just think it out. Yeah, I think so. In this problem, it asks you to find. Let's see what is the drift? What is the drift speed? What is the drift speed inside inside the copper wire? Inside the copper wire. So n is the atom per unit volume. Atom per unit volume, which is the carrier density, So atom per unit volume. So it can be separated as atom per mole, and then mole per mass, and then mass per volume. So in this sense, you can see the cancellation here is like mole and mole can be cancelled, mass and mass can be cancelled. So it turns out to be atom per volume. And why we need this? Because we have mole per mass. Mole per mass is the reciprocal of this value. And then mass per volume. Mass per volume is actually this number. So we can get this number and this number. And yeah, and atom per mole is actually this Avogadro number. So actually we can get all these three numbers to calculate the carrier density. So which is Na times 1/m times the roll copper. Okay. So we have this expression, and yeah, so we can just plug in the values. So it is 6.02 times 10 to the 23rd power, and then times the molar mass, the reciprocal of the molar mass, 63.54, and then times 10 to the minus third power. Because this is gram, we need to convert it back to kilogram. Oh yeah. So we need to we need to times 10 to the minus third power to it. And copper here is, yeah, it's like times 8.96 times 10 to the third power. You feel it is quite strange because this is gram. If we need to change it to kilogram, it is like 10 to the minus third power. But here we have centimeter cube. So centimeter cube is 10. Is like 10 to the 10 square and then cube, something like that. Because this is in the denominator. This centimeter cube is at the denominator. In order to make it a meter cube, we need to multiply it by 10 square and then take the cube of it. So overall, it is 10 cube. Okay, so we will get this value to be 8.49 times 10 to the 28th power meter per meter cube. Okay, so this is the carrier density, and we can make use of VD equals J over NE. If you still remember this equation, just now it is up here as J equals NE times VD. The current density is proportional to the drift velocity, so we just move NE to the left side. Okay, so J is, so here we have a J equals I over A. I over A. So we have I over NEA. So I is 17 milli, 10 to the minus third power. And then N is what we have calculated is 8.49 times 10 to the 28th power. And then E is the elementary charge, 1.6 times 10 to minus 19. And then A is this one. A equals pi r squared. So pi times 900 times 10 to minus 6 quantity square, like this. So the value will be 4.9 times 10 to minus 7. 10 to minus 7 meter per second, which is really, really low. Really, really low. So I put it here. Lower than a snail. 慢嗰隻蝸牛啊！ So you may feel strange if you just switch on, just switch the light. When you just press the button, then the light will turn on, feel like immediately. Something like if you just push the button or switch it. So suppose you have a light. If you just push it, you feel like it turns on immediately. But how to explain the drift velocity of the charged particle moving so slow? It is like actually the wire are full of carrier, the charge carrier. So even though it moves very slow, it's just like queuing up many charge. So even though for a millisecond, it's just move forward for less than a micron, but it moved for this, and then the charged particle here move for this. So it's just like pushing the front carrier to the electric device. So the drift velocity can be that slow. Okay, so next we introduce the variable called the resistance and resistivity. So if we apply the same potential difference between the end of geometrical similar rods of copper and of glass, very different current results. So now, of course, you know the copper is conductor, the glass is isolator. Of course, they will be the current will be quite different. So the characteristic of the conductor that enter here is electrical resistance. So it introduced this variable to explain this phenomenon. The resistance R of a conductor is defined as V over I. So V is the potential difference over the device, and the current I is the current going through it. And of course, the SI unit is ohm. So actually, V equals IR is the well-known formula called the Ohm's law. So where V is the potential difference across the conductor and I is the current through the conductor. So nothing special here. Okay, so yeah. So actually the R relates to the material itself, and also related to the geometry. of that conductor. So the cross-section area and also the length will influence the resistance and also the material. Like this one for the copper is this conductor, so the resistance will be small, and if it's isolated, the resistance is large. Or if it's silver or gold, the resistance will still be different, even though the geometric state is the same. And if it is still, if we have still two copper wire with different geometry shape, then the resistance will still be different. We will explain it later. So here we also introduce another variable called the resistivity. So just now resistance is R. Resistivity, we denote it as rho. So rho is E over J, E over J. Or if you write it in the vector form, it is E vector equals rho times J. This is called the vector form of Ohm's law. Vector form of Ohm's law. So the decision like this expression. Of course, the engineer don't like this. Engineer try to simplify things. The decision try to make things complicated. So I seldomly use it, but my physics professor really like this expression, and actually I seldomly use it. So rho is E over J. So the SI unit of it will be ohm per meter. So you can simply check it. So if you still remember, the SI unit for E is V over M. And then the SI unit for J is I, if you still remember, I equals JA. So the SI unit for J is I over meter square. So V over I is V over A. It should be A. The SI unit for the current is A, ampere. So V over A is ohm. V over A is ohm. If you still remember, V equals IR. So this is A, this is ohm. This is V. So V over A is ohm. Okay. So meter and meter square canceling it becomes meter. So we have this one. Okay. So here we define a variable called the resistivity, denoted as rho. And rho only relates to the material itself. It doesn't relate it to the geometry shape at all. And the reciprocal of the resistivity is called the conductivity, which is denoted as sigma, which is 1 over rho. Okay, so just define some variable only. Okay, so yeah, so let me finish here today.